Hello, my name is Jason Masterakos. I am the owner of STEM Online Academy. For those of you who don't know or who might be new subscribers or viewers, STEM Online Academy is a channel in which we talk about uh, advanced mathematics and physics concepts, both not just concepts themselves, but also going specifically through rigorous problems. Okay, this is for anyone in the niches of undergraduates, graduate students, and or researchers. They would be interested in my work. A bit about me, if you already don't know, I am both a mathematics specialist and a physics specialist. I got my undergraduate from Carleton University. I'm very well versed in these subjects, and my approach to helping people has always been using a three-pillar technique. And that technique for solving complicated mathematics problems is by one, making sure you understand the problem semantically from what you're reading, whether it's a word problem or a complex equation, make sure you're understanding what is being asked. Once you understand what's being asked, you move to step two, which is to make sure you utilize uh, geometric modeling. Okay, what I mean by that is you should be able to graph the equation or problem that you have, equation or word problem, whatever it is, right? Or a numerical problem. And once you're able to graph it based off of the information you've extrapolated from step three, you move to step three, and that's developing a mathematical equation for the model. Because from there, once you have an equation, you can use a particular mathematical method to solve it, which is usually easy. It's not always easy, as you will figure out from my book, Advanced Integration Techniques, where no mathematical method is truly that easy. Okay, so trust me, there's easy sections too. It's all complicated. But yes, we're going to talk about that stuff. Okay, so let's get right into it. Okay, so what we're going to be looking at today is going to be an interesting sequence of events. Okay, so what do I mean by that? Well, if we go to, just give me 1 second. Let's go to my whiteboard here. Okay, I'm going to discuss what we're going to be looking at. Okay, so let's share the screen. Okay, let's go to the entire screen. Okay, just one moment. Let's get the whiteboard up. Okay, so if you can see my whiteboard, what we're going to be talking about is something very interesting. Viewers today in this live stream are going to submit to me your hardest mathematics/physics problems. Okay, and it needs to be, now, not any problem, it has to be relevant to the material of this book. Not necessarily exactly from the book, but what I mean is anything to do with integration, numerical methods of integration, complex methods of integration, um, anything around calculus. Does have to be pure integration, limits, derivatives, whatever it is, and or some physics problems, which are mainly, well, I don't want to say physics problems, where the math is applied into physics, where calculus is applied into physics. Okay, so if you have any of those problems during the live stream, you can send it through the chat. Let me explain how that's going to work. So what you're going to do is, if any of you are there, you're going to pitch to me any problems that you have in the chat, right? So just type in anything, whoever it is, type in any problem that you are actually struggling with, okay? And I'll try to go through them as many as possible. Well, depending on how many people we have here, we have to be realistic. I won't be able to do all of them, obviously, but I'm going to choose at random. Okay, I'm just going to choose at random which ones to do, and I'll explain step by step on the whiteboard here, okay, through both a visually spatial approach and a logical approach of step by step of how to solve the problem to the best of my ability. Okay, so that's what we're going to do in this live stream. We're going to have you guys pitch to me your hardest problems, and we'll just go back and forth. I think that'll be very handy. Okay, so we're going to do that. All right. And another thing we're going to do, that won't be the entire live stream. I'm going to show you, this is today's list. I just put everything down in order. I hope that's handy. The next thing we're going to do after that is I'm going to show you a demo showing a 10-dimensional sphere in hyperspace. Okay, I just want to show you something very cool because it's relevant to my book, Advanced Integration Techniques, right? By the way, for those of you who don't know, the book Advanced Integration Techniques is where we master advanced integrals and applications, okay? All right, so you're going to learn very comprehensively lots of different integration methods about this book, right? So if you're interested in that, you can always check out in my channel. In my channel is a direct link to the book if you're interested in learning more about it, okay? All right, so we're going to be looking at a 10-dimensional sphere because there's a specific problem that talks about that, okay? And then after, so I told you on how you're going to submit the problems, talked about 10-dimensional spheres that we're going to model in hyperspace. And then you're going to submit your problems in the chat, and I will solve and explain on the whiteboard. I'll do that. Maybe there'll be some of you who already know how to do it and submitting to me right now. But preferably, I'm going to go through first the 10-dimensional sphere, talk about it. Then you will submit. I'll look at reviewing your problems, solving on the whiteboard. Okay. All right. And as I mentioned, I will choose a random, any random question of the viewers. Not only that, I'll also put one of you, at least one of you on a live call to discuss the question in more detail. Okay, so that's why there's more of a face-to-face interaction. Okay, the less face-to-face interaction, the less interaction verbally. Also, it becomes a bit robotic. I don't want that. Okay, still believe in face-to-face interaction, even in this digital age that we're in. Okay. All right. So let me see if any of you are at least coming in. I just want to see. See a sec here. Go to the any of you there. Okay. All right. Nothing yet. I guess some of you are coming in late. All right. So that's not a problem. Yeah, that's not a problem. So if any of you have any inquiries when you're coming in, just let me know. Again, this live stream, you'll be able to share any questions that you have, any difficulties that you have, and I will take them up to the best of my ability. As I said, I can't do all of them. I'll try to choose a few at random, and we'll go into details of the problem. Okay. All right. So let's go back to the whiteboard if there isn't any questions at the moment. Okay. Okay, let's go back to the whiteboard. So I want to show you guys something very interesting that you may find handy. Okay. All right, and we're going to be looking at this simulation. Okay. So I created a computer simulation of a hypersphere. Now, why am I talking about a hypersphere here? There's a specific problem from my book, okay, and which I thought was interesting bringing up, and that's calculating the volume, right? How to calculate the volume of a hypersphere, okay? And that formula is this that you can see right here, and it states that capital V of n, V is the volume, and number of dimensions, is equal to little pi all to the power of n over 2, right? N over 2 power, divided by the gamma function, all in parentheses, of n over 2 dimensions plus 1. Okay? By the way, it will help if you have, note, if you have a background in integral calculus and linear algebra at least, okay? So that's why you're understanding what I'm saying, okay? Because some of the terms I use, some of you have noticed in my live streams, are very technical and precise, and if you don't have some of the background, it could be problematic, okay? So make sure you're well-versed in integral calculus and linear algebra, okay? All right, so we're looking at this formula here, okay? And what we're going to do is we're going to apply it to 10 dimensions. So let n equal to 10d, okay? So what this is saying is we're having a hypersphere in 10 dimensions. Now, obviously, like numerically, it's pretty easy to calculate. You just plug in n equals 10, right? It's nothing. I'm not doing anything brilliant here. I'm just putting n equals 10, right? So I'm just putting in the specific value into the formula. Very easy, right? Now, the very hard part is visualizing a sphere in 10 dimensions. I can't do that, okay? And I'm sure most of you won't be able to do it either. There's certain methods, something called slicing, if you've ever read The Shape of Space. I haven't read that book. You may want to refer to it. I may want to refer to it. Something called The Shape of Space, but it's a bit complicated. And there's another book called Flatland, okay, which also talks about how to visualize things in higher dimensional space. Once you get to 4D, it gets very complicated, and after, so 10D is crazy. That's why I'm using a simulation, a computer simulation that can give us how it looks like in 10-dimensional space, okay? All right, any questions? I want to stop talking. I want to see if you guys have any questions so far on what I am discussing. Let me see here. Anyone have any questions on the dimensions and anything I'm talking about right now, how it relates to any courses you're taking? Okay, so we have one person. One person is asking. He's asking as it relates. What are these dimensions? How are they important, and what are the applications? Well, yeah, good question. The applications for an equation like this would be in probability theory, okay? Because quite often you would need to do some modeling, statistical modeling with the gamma function, okay? The gamma function is very important because the gamma function is related to factorials, n factorial. Actually, it's n minus 1 factorial for the gamma function, okay? So that's one application. Another application of the gamma function, or are you asking specifically the exact formula I put up, or just the gamma function? Okay, so whether it's the gamma function or the specific formula I put up, they both have applications. I think even in I put an application in my book near the end, something called a Feynman's path formulation. Now I'm elementary, very elementary in quantum physics, but I don't have enough background, but I do know an application of the gamma function that I put in my book here. Okay, so it applies to quantum physics, which is really interesting. Okay, so there is an application of the gamma function there, in science and in statistics and probability and statistics. Okay, now let's go back. Okay, so I want to go back to the web. Okay, so as you can see here, this is how a 10-dimensional sphere looks like. In other words, a hypersphere, a volume of 10 dimensions. Okay, you can see that you have multiple rings. Normally, if you have a sphere, it has one horizontal ring on the plane. Let's say if you had an XY plane. Okay, and then you have the circular disc from the vertical axis going all the way down and intersecting the other axes. Now, in 10 dimensions, what you can see is you're having multiple rings and all sorts of concentric planes, like different planes. You can have maybe X, Y, Z, T, or W into the fifth dimension. You would have to invent more variables as you go up more and more dimensions. Okay, but I hope that this simulation is helping your visual spatial skills. Okay, right? Maybe not immediately, but in a way, getting your mind thinking on how to visualize higher dimensions. Okay, right? So that's why next time when you have to deal with anything like that, you can sort of say, okay, maybe this is approximately how it will look like, right? Some ideas will come to your head. So that's the point of having the simulation, making it easier for your creative juices to flow. Okay. All right. Now, what is this formula specifically for the V of n? Okay. Well, it's a volume of an n-dimensional unit sphere. Okay. All right. That's all it is. Volume of an n-dimensional unit sphere. Specifically, what we're going to be looking at today is the n equals 10 dimensions, as I mentioned. Okay. Now, what's interesting about this formula here? Okay, the V of n, which is that I have there, is that the volume grows initially. Okay. However, once you get to n equals 5, it caps. Does anyone understand what I mean by caps? Let me see if anyone in the chat understands what I mean. Okay. So what does that mean? What does that mean that V of n at n equals 10 is capped off? Any questions? Okay, so there's no questions on this specific thing I'm talking about. There's no, in other words, there's no misunderstanding, I hope. Okay, good. Okay, let me just go back here. So what that means is we're at an inflection point, right? So initially, right, as I mentioned, right, the volume grows initially for any n-dimensional hypersphere, okay? In hyperspace, the volume grows initially, but then it's going to peak around at n equals 5. So when you have a dimension of 5, the volume will peak, okay? And as you increase dimensions, n greater or equal to 5 dimensions, it's going to shrink to 0, okay? So your volume will start becoming smaller and smaller as you increase n. Now, as I said, that only happens when n is greater or equal to 5, okay? So the volume will decrease as n decrease and approach 0 as n is greater or equal to 5, but its dimensions obviously are increasing because if n is greater or equal to 5, the dimensions are increasing. All right. Now, what we're going to do later on in the live stream, unless you guys at some point are giving me questions that you're having trouble with, we'll divert from this and we'll go to any calculus or physics questions that you have. We'll look at not necessarily proving this formula, but we will look at validating this point right here, that a 10-dimensional hypersphere always has constant volume of 2.55. Okay, in other words, we'll numerically calculate at n equals 10 that we should get a volume of 2.55. Okay? All right. So this is going to be very fundamental for the understanding of higher dimensional geometry, and I think even machine. I didn't put any in my book. I didn't put any applications for machine learning. But yeah, there is some applications in quantum physics. When I made that book, I did a lot of extra research. There was a lot of things I had to really study, do a lot of questions, do a lot of stuff, and go through everything, and also learn some new stuff too. Right? Initially, I didn't know a gamma function was applied in quantum physics, but it does have applications in quantum physics actually. Okay, which is essentially applied mathematics. All right. All right. And as you can see down here in the simulation, not only did we get a uh, really cool simulation, I think it's cool. Geometrically, it's nice to look at. I think you guys would agree, right? Anyone agree? Yes, I see some people interested in the simulation. Yeah. Okay. All right, let's get back. Let's get back to it. Okay, so let's go to back to the simulation. Just one second. Okay, so let's continue off. So as I was saying, not only did we get a nice simulation, but it also gave us what happens, like a chart, which is very organized, showing the dimensions from one dimension to 20 dimensions, the formula, the volume, depending what R is, R equals 1, surface area and volume ratio, right? So you can see, since we're interested at 10D here, right? Our formula for that, our formula for the volume of a hypersphere, an n-dimensional space, should be pi to the 10 over 2 over the gamma function of 6. Okay. All right. So you'll notice here that we get 2.55 will be the volume. Okay. 2.55 will be the volume according to our computer simulation. That's what it's saying here. Right. All right. So 2.55. And surface area is supposed to be 25.5. I have to verify that. Okay. That's what the AI is saying, but I'm going to verify it on the board doing the numerical mathematics on the board and see if we get 2.55. Okay. All right. So that will be interesting to compute. All right. Some other things that I think will be handy, right? Oh, I also forgot to mention this is handy. You can see that the visualization. Anyone have any questions on the visualization here? Right. I know it's a 10-dimensional hypersphere. I've talked about that, but is there anything else you want to discuss on the with the projection? Anything on the projection? Any questions on the projections? Okay, so nothing wrong. So we notice that we have as I mentioned above, right? Our 10-dimensional hypersphere. Um, you can see that this visualization shows multiple. That's what it is. That's a very precise word to use. Multiple perspectives on the 10-dimensional hypersphere. Okay. You can see that there's multiple volumes of evolution, and you have multiple dimensions crossing the 2-dimensional cross sections, right? Those circular disks are 2-dimensional cross sections, but you have multiple 2-dimensional cross sections. Okay. So another way to think about it, if each one of these are in 2 dimensions, those circles are, every circle is in 2 dimensions, and we have 10 of them, right? So you just do 2 times 5 gives you 10. So 2 by 5 gives you n in this case, total number of dimensions. Okay. All right. Now here, what I want to show you, if anyone doesn't have any questions on what I just said, Let me make sure. Anyone have any questions? There's no confusion. Any confusion, or there's no confusion? Let me make sure. And make sure you guys are understanding. Okay, so far things are good. I think there's any misconceptions. Not really anyone's showing up today. That's okay. Last week there were like 2 or 3. There was like 3 people. Well, that's fine. Maybe some of you will come later. It's a pretty long live chat, so there's still time. Again, as I said, we'll be talking about the n-dimensional hypersphere from my book. And if not, if anyone has any mathematics, physics, or problems, give me your hardest problems from that's somewhat related to what we're talking about, integration, or anything of that nature, right? All right, so let's get back to the whiteboard. All right, so if you look here, right, okay, now we're going to look at it in a 2-dimensional projection. Okay, so if we look at a graph, okay, this will be relevant. I know it doesn't look relevant at the moment because we have a 10-dimensional sphere. 10-dimensional sphere, the simulation that I brought up. So here we have a volume versus the rate probability density. Okay, so looking at the graph here, okay, you can see that it's sort of somewhat of some sort of a bell curve like shape. Okay, has to be because it's related to the gamma function, and the gamma function is due with exponential growth. Not exactly exponential growth, but you know what I mean. So this curve here is going, it goes up, and then it really spikes up here. If you pay attention to this portion here, it spikes, comes back down, moves again, spikes up, comes down, moves again, spikes up, and then comes down. Okay, and it constantly descends downwards afterwards. Okay, completely descends until it intersects the, let's say, the probability axis. Okay, as you can see here. All right, so you can see that there's spikes. It comes almost like it's a shifted bell curve with really upward spikes here, right? So it really spikes upwards and comes down as a regular bell curve, spikes up, it really spikes up, comes down, and spikes again. And there's a decrease in height in terms of the spikes in volume, as you can see, right? Which makes sense because that is consistent to what I said earlier, right? If n gets greater or equal to 5, right, the volume will start to decrease and approach 0, right? So as you can see here, as n is greater than 5, so here's the peak at n is 5. Then after it starts going down, down, down as n gets higher and higher and higher, right? It should be approaching 0, and that's why it intersects the axes. Okay. All right. Over. Any questions on that? Okay, so then over here we have a 2-dimensional cross section, right? This is just looking at each one of those disks from above, if that makes sense. So what I mean is we're taking some sort of a panoramic view. I'm translating from a 10-dimensional sphere, which is complicated, to looking at individual circles, concentric circles, right? So each one of these 10 circles overlapping each other, right? As a 2-dimensional projection, as opposed to a 10-dimensional hyperprojection, that which gets complicated, okay? So you can see we have cross-sectional projections here, okay? So one that's a 2D, 4D, 6D, 8D, and 10D. As you move away from the center point here, okay, your radius will increase and you're moving away. One is in, the first one should be in 1-dimensional space, 2 dimensions, 3, 4, 6, 8, 10, whatever, up to 10 dimensions, okay? Finally, we also have this guy over here. Now, this is a bell curve, okay? For those of you who've taken any probability, you should know some basics of probability, right? Okay. From probability and statistics. Can anyone tell me this bell curve? Yes, it's a bell curve, but what equation models this? Does anybody know? Let's look at, let's see if anyone knows here. So you can see that we have a bell curve there, okay? Very interesting bell curve, but what does it represent? What does it mean? What type of distribution? Hint, hint, distribution. Anybody know what type of distribution? Nobody knows, I'll go back. Okay, so this would be a bell curve is modeling the normal distribution, a probability distribution, right? Okay, right. So it's just calculating the normal distribution, which is a standard normal, any probability density function, right? Let's say probability density function p of x equals e to the x minus mu all squared divided by 2 sigma squared power, right? Where x is some data point, mu is the mean, certain certain mean away, and then divided by sigma squared. Sigma is the standard deviation. Standard deviation away from the mean, plus or minus away from the mean, right? So if you look back here in the drawing, that's why I like to use models a lot, even for whether it's the easiest or most advanced or abstract math equations. This is why I like to use graphs a lot, because you can sort of relate to it, make sense of what's going on, right? And it brings math to life. Okay, so let's go back to right here. Okay, see, this is a bell curve. Okay, in this case, the mean is the center point here, this vertical dashed pink line, right? And I'm moving certain number of standard deviations away from the mean will tell me that's what the standard deviation is. Okay, all right. I won't talk about cell concentration. I think that's not as important. And what we'll do soon is we will try to verify this 10-dimensional volume of 2.55. Okay, as close as possible. All right. Also, some other important facts about our hypersphere, okay, is comparing volumes. So that's in 10 dimensions. If you were to compare volumes, let's say if n was 1, okay? If n is 1, geometrically, does anyone know what that means? So if I chose n to be 1 dimension, what does that mean? What shape what shape would it be if n is 1 dimension for the volume? 1 dimension. This would be a line, right? A line of distance 2r radiating from both sides, because n is 1, right? If n is 1, it just has to be the one-dimensional case of a line, right? Think about it. If n is 2, then what would it be? If n is 2, in terms of the volume, what would it be? What type of shape? Does anybody know? Come on, guys. If n is 2, it would be a circle, right? 2 dimensions, right? It has to be a circular disk. What in that case, the area would have to be pi r squared. Okay. All right. So I hope you're seeing how that works. Okay. And as I said, this can go up from 1, 20. Doesn't matter how many dimensions we have for hyperspheres. It can be n-dimensional hyperspheres, right? All right. Now, as I've mentioned before, right, and the simulation also picked up on it, right? You'll notice that we have a near peak at n equals 5, right? So I just want to use a more precise word here. You already know what it is. That's the word. Exponential decay afterwards, right? From n greater or equal to 5. N equals 5 is at the peak of this curve here, okay, at 5 dimensions, right? At n equals 5 dimensions, the volume is at its peak, okay? That's the highest it can possibly get. After n equals 5, you'll notice that the peak descends. We have exponential decay at n equals 6 dimensions, 7 dimensions, 8, 10, 12, 20, doesn't matter. Major exponential decay, right? Approaching zero after once you've reached the axis, once you've approached the axis, okay? I don't want to say approach. I want to say intersect the axis. Once I've intersected the axis is the correct phrasing. Once I've intersected the axis, then I will approach. I'll get to zero volume. Okay. So remember, it's very important for when it comes to the behavior of this equation. Okay, is that it peaks near n equals 5 dimensions. After n equals 5, there's major exponential decay of the volume, right? Which means that the volume has to be, does anybody know? Exponential decay? Decreasing, right? Because if there's major exponential decay, the volume has to be decreasing. All right? So you're going to have major exponential decay. All right? And not only that, as the volume decreases, what do you think happens to the number of dimensions as the volume decreases? Volume decreases. Look on the dimensions here on the graph. Well, it's to be obvious, right? As the volume is decreasing, number of dimensions increases. Okay. All right. I think that is good. I think we've covered a good amount when it comes to understanding what this is. Okay. Oh, one last thing I really want to discuss here. Okay, and that's the link to Gaussian integrals. So for those of you who have a solid, pretty solid foundation on, integral calculus or anything like that, you should know what a Gaussian integral is, right? That is just finding the area under the curve. Okay, right? It's just finding the area under the bell curve is what a Gaussian integral is. That's integrating the probability density function, e negative x squared. Okay. So, and there's a way to derive that using, we can derive actually this volume of n-dimensional hyperspheres actually. Okay. Using Gaussian integration. I might do that in a regular video next time, not a live video. I don't want to get into that. That's not the main focus of this live stream. This live stream is to discuss, obviously, the volume of n-dimensional hyperspheres as a geometric simulation, and also to discuss any questions that you guys have when it comes to any calculus questions you may have, or anything else for that matter that's somewhat related to this. Calculus or physics questions. Mainly when it comes to physics, please make it something that's more math-based physics. But yeah, that'll be helpful. Okay. So yeah, I just want to show you how it's related to the Gaussian integral. Okay, so it's really nice looking at these curves. All right, so let's get back to the regular whiteboard. Okay. All right, so I've discussed showing a 10-dimensional hypersphere. What we will look at now, okay, I haven't put it down since I'm not getting any specific, very hard, challenging questions that you guys are having trouble with in either your classes, your university lectures, or or anything else for that matter. Or if you're even don't have to be a university student, you can be a person who's enthusiast trying to teach yourself this stuff, and you came across a problem and you're stuck on it, and you're like, how on earth do I integrate this? Right? So if you're having any of those times where your head is stuck and you're getting annoyed with the problem, please send it to me. I'm always available. I'm available now. This is the best time. I'll also talk about my office hours on Fridays. Okay. Let me see if anyone in the chat. All right. Anyone in the chat? Not at the moment. Okay, let's get back. Yeah, let's get back to the whiteboard. Okay. Okay, so what we're going to do is we're going to, since there's no emergency questions that anybody has, we'll go directly to solving this guy right here. Okay, we are going to solve this volume formula that I talked about, which calculates volumes in n-dimensional hyperspace. Okay, of n-dimensional spheres. All right, so V of n, volume, is equal to pi to the n over 2 power divided by gamma of n over 2 plus 1. Okay, now what we're going to look at is at n equals 10 dimensions. Okay, looking at n equals 10 dimensions. Okay, I'm going to say at, I'm going to use a different color here. I'm going to use it at n equals 10. Okay, at n equals 10. Just 1 second. At n equals 10 dimensions. Okay, just put it down there. Now, another thing I want to talk about, and I think it's very important, okay, because there's multiple things that whether you're a high school student, university student, doesn't matter who you are, or if you've taken math, you've experienced this, and it's very important that we talk about it, is there's one thing knowing how to compute things, like calculations and stuff like that. That's easy, right? You just put it in the formula, anyone can do it. But there's another thing to conceptually understand things geometrically, and to conceptually understand things also, what the math means, what the formula means. Okay, we talked about geometrically what this formula means. Okay, and as you know, it's not easy to visualize things in 10 dimensions. By no means is it easy. Even 4 dimensions, already your head is starting to bleed if you try to visualize 4 dimensions. Yeah, it is very tricky. Okay, unless you turn into Einstein all of a sudden and you're able to visualize 4 or 5 dimensions, but no, I can't do that. Anyways, my point is that I want to talk about understanding this expression, and I wrote some stuff down that I want you guys to not only listen to what I'm saying, but also read it as well, so you can get a solid, comprehensive understanding of what this equation actually means, right? So as I've already mentioned, right, in this problem, we're finding, okay, all we're doing is finding the volume Vn, right, V sub n, of an n-dimensional hypersphere of radius r. Any sphere has constant radius r. I don't think there's any dispute on that. Anyone have any disputes? Anyone have any disputes on what I said? Please let me know if anything is tricky, contradictory, or anything else that you found. Anybody? Okay, so if there's no difficulties, nothing whatsoever, we can continue with the problem. Well, understanding what it is, right? Okay, let's go back. So as you can see here, right, we have in the 1 dimension, right, In one dimension, for instance, I already talked about this, we will have a line segment, okay, extending a distance, capital R, in each direction radially, okay, such that its length would be V1 equals 2R. Now, I'm letting V be area in this case, okay? Well, I'm going to transition from volume to area. I'm just going to use capital V sub n. V sub n will be different than just using V, because depending on what n is, what dimension n is, that will determine if it's going from two-dimensional space area to three-dimensional space volume. So I'm just using V sub n is the most accurate instead of area A. Area A would not be precise enough. It wouldn't be written precise enough if we used area A, right? Because what if n is 3, 4, 5? Then we're getting three dimensions, and then we're getting to hyperdimensions, and that wouldn't be accurate. That wouldn't be a cross-sectional area. Okay. All right. So, yes. So at V1, at n equals 1, will be 2R. Okay. At n equals 1, it's just going to be 2R. Okay. At n equals 2, n equals 1 is a line. N equals 2 is a circle. Right. So you're going to notice some sort of interesting pattern here. It goes from V sub n, right, was 2R at n equals 1. N equals 2, V sub 2 of R will be pi r squared. Pi r squared, you already know, that's a circle. Right, just a regular two-dimensional circle. Okay. All right. And if we were to continue, I've listed them all here, right? I tried to put it in more order here. So at n equals 1, V1 of R is 2R. My distance of a line segment, V2 of R would be pi r squared, right? So area of some sort of circle. And then V3, 4/3 pi r cubed, which would be a sphere. Okay. So as you can see, there is some sort of relationship here. Okay. You'll notice that there is some sort of increase in R, like R to the n when n is 1, 2, 3. So you can say that V sub n. So there's a pattern here that's actually being produced depending on whatever n is for hyperdimensional spheres, right? So if we were to continue on, dot, 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 right? We should get, just 1 second. We should get V sub n of R, right? V sub n of R. Actually, I'm going to ask you guys. I'm not doing the heavy lifting all the time. Based on the pattern of our n-dimensional hyperspace for a sphere of n dimensions, what would it be at V sub n? There should be a generic formula for this. And there's no point in me putting the formula unless I test you guys and see if you're understanding it. That's right. I'm not going to give you the formula. I'm going to wait and make sure you see if someone can answer the question. Okay. So again, right? As you can see here, at n is 1, n is 2, n is 3, up to, let's say, n being number of dimensions of R. What would be a generic formula V sub n of R? What would it be? What will it be? Have any questions? Anyone know? Okay, so you are having some trouble, it seems. I'm not going to write it up on the board. I need to make sure you guys are understanding. So if you have But what I can do is I give you some hints and maybe some sort of process and how we get there. Okay. So if you look at v sub n of r, right? Right. So we stated that n equals 1, we will have a distance of a line segment. Okay. N is one dimension. It should be a line segment. Okay. Let me put a drawing here. Okay. So this is, maybe this will help. Okay. So n is 1 is a line segment. Okay, this is at n equals 1 dimension. 1 dimension, I have a line segment. Okay. At n equals 2 now, n equals, I'm going to use a different color. Using the same color can be boring sometimes. Okay, n equals 2. Okay, n equals 2. Right, n equals 2 dimensions. Right. Now we get a circle of area pi r squared. Right. Okay. Obviously, right? Since we're dealing with n-dimensional spheres, right? At n equals 2, it's no longer a sphere. The dimension's 2D, so the two-dimensional sphere is a circle. I hope that's making more sense the way I phrased it, right? N-dimensional sphere at n equals 2 dimensions is a circle, okay? So this is now a circle. Okay, so we have a circle here. Right. Again, don't feel shy to ask a question. Okay, so we have n equals 2 here. Or if you know the answer, please go ahead by all means. So n equals 2. So n equals 2, we have a dot, right? Right at the center of the circle. Let's say from point O, right? To the end point, point P, okay? Here's point P. And this will be length OP, let's say. This is length OP, and OP has radius R, okay? So this is capital R, all right? Anyone following so far? Okay, good. Okay, so that's in that's going to be in a two-dimensional space. Okay, then as I said, for n equals 3, okay, you can see already one pattern. I'll give you a hint. One easy pattern is that r to the power of something is increasing. This is r to the first power. Okay, at n equals 1 dimension. R equals 2 the second power at n equals 2 dimensions. R equals r to the third power at n equals 3 dimensions. Okay, so n equals 3 dimensions. So at n equals, sorry about that, at n equals 3 dimensions. So we're going to do n equals 3. Okay, what we get now is a cool sphere, 3-dimensional sphere. Okay, so I'm going to use a okay, so we have a 3-dimensional sphere here. And as I mentioned, a 3-dimensional sphere just has one 2-dimensional circular projection, right? If we were to graph this on an XYZ plane in 3 dimensions, right? Okay, so you have this. Let's say this is X, Y, Z axis, okay? Right, you have these projections down here. I'm extending the axis to so that it's going in both directions, multiple directions. Okay, you have something like this. This would be a sphere, okay? All right. So I hope you're following along, and you see that the pattern is still continuing at r to the third power. Now, at v sub n of r, what would be the generic formula given the pattern here? Well, it will be something like this, right? It will be, let's say I call, well, these parts are always constants. They're independent of r, right? This is a constant, right? 2 is a constant. Pi is a constant. Pi is a constant because it's 3.14, 3.14, so forth, right? 4/3 pi is a constant. That's a number, right? Only r is changing. So I'm going to say, in reality, let k be some constant, okay? So k is some constant. K times capital R for radius, r to the n power, okay? Right? Right? Because when n, if n were 1, that would be r. That would represent the first segment, the distance of a line segment, v1 of r, where we got 2r, okay? And then when n equals 2, we'll get r squared, n equals 3, three-dimensional space, r cubed, okay? All right. However, though, we still have an issue with k. This is not that easy to spot this pattern, actually, because k, I'm just saying k is a constant, but it doesn't take care of the change in the constants. Look, we went from 2, then we went to 1, sorry, not 2, 2 to pi. So we went from 2 to 3.14 to 4/3 pi. Okay, so we need some more information on the k. Does anybody have any ideas? Well, this is what's going to help. Okay, we're going to so I'm going to specify this k here. So k is a constant first off, right? So k is a constant. Unless anyone has any disagreements. Anyone have any disagreements on this? Okay, if no, we can continue. Okay, so k is a constant. K is a constant. Constant. Okay. Not only is it a constant, which is independent of the radius, independent of the radius, but it is also affecting. It's a constant that is scaling the pi. Okay, so which is scaling pi. Okay, so what you will get here for this k, all right, in reality, it should be something like this. Okay, let me just write it out here. We should get v sub n of r is equal to, let's say I'm going to use, it's okay, I'll use k sub n minus 1 times r to the n. Okay, where k sub n minus 1, right, is wherever your dimension is, all right, whatever your dimension is. Let's say if n is 2 here, 2 minus 1 would be k sub 1, and this would be r2, right? So you're going to be decreasing this scalar constant pretty much, okay? All right. Just waiting for anyone to question me on anything, okay? You won't have any disagreements, anything at all that is giving you a hard time. Because I don't want to zoom through things fast. This is a live stream, right? So my job is to make sure I'm pausing and waiting, right? Not just rambling. Anything at all. Okay, so let's continue, right? So k sub n minus 1, I'm going to say exactly what this is. A constant constant volume. So k sub n minus 1, I'm going to put it over here. So k sub, right, so let k sub n minus 1 be unit volume, okay, unit volume, right, such that k sub n minus 1 is equal to k of 1. In reality, this is constant unit volume. That's what it is, right? K sub n minus 1. Doesn't matter what I call it. I can use v. But I'm just using k sub n minus 1 to be a unit volume, constant unit volume. Okay? So k sub n minus 1 is k of 1. And turns out if you take the unit volume of anything, right, it's always equal to 1. Okay? If you had k of 2, it would be different. K of 3 would be different, and so forth. Actually, that's what we're going to talk about, not in the live stream, but in my next upcoming video. Okay, that's why I've done this live stream a certain way, because I want to talk about these concepts geometrically and numerically when it comes to calculating the volume of n-dimensional hyperspaces, and try to lead into the next video of next week, this coming week actually, on proving this formula, which is not easy, and it gave me a headache when I tried to do it a couple of years ago. But I'll walk you through it, and it's actually pretty fun. Okay. All right. So let's continue. Okay. So we're going to move on to the last part of this section when it comes to calculating n-dimensional volumes, okay, in a hyperspace, unless there's any questions. Any questions on this, or any questions you guys have difficulty on when it comes to math or physics? Specifically math, because this, I want it to be somewhat relevant to the concepts I'm talking about. Doesn't have to be a gamma function. I'm just talking about something calculus relevant, right? It would make sense, right? If I was doing, let's say I was doing something on, I don't know, on rock and roll or algebra, the questions should be relevant to that specific live stream, right? But since this is calculus based, I would prefer being calculus. Maybe a physics question that involves calculus, but yes. But yes, shoot me any of those questions that you have difficulty with, and I'll go through them. Okay, so nobody yet has anything. Okay, so either we have an extremely smart audience that is filled with know-it-alls, or it's today they're finding it somewhat boring. Okay, so let's go back. Let's go back to the whiteboard. Okay. Okay, so we're going to talk about the last thing. Okay. One of the last things, maybe the last thing, but it takes some time doing, at least calculation-wise. Okay. But we want to verify some calculations here. Based on what the AI simulation gave us, it told us that apparently at n equals 10, we should be getting a volume of a 10-dimensional hyperspace to be approximately 2.55. I will verify that and see if the AI is making sense or if it's talking nonsense. Okay, so let's do that right now using the formula from my book. Okay, so go to the third section here. So now I'm going to calculate at n equals 10 dimensions. Okay, so let's do calculating at n equals 10. Okay, so let me just write it over here. Now we will calculate. Okay, so we will calculate. So calculate. Calculating. So we're going to calculate n-dimensional hyperspace. We're at n equals 10 dimensions. At n equals 10 dimensions. At n equals 10 dimensions. Okay, so we're going to calculate at n equals 10 dimensions here. Okay. Now we're going to need to think about this at n equals 10 so we're going to use our interesting formula here, okay, which states that the volume of any n-dimensional hyperspace, right? So we're going to calculate at, so here's the solution at n equals 10, okay, at n equals 10, okay, we're going to use v sub, so capital V of n, remember what it is equal to pi, just 1 second, pi to the n over 2 power. I need to make some space here, so we're doing it at n equals, just give me a moment, at little n equals 10 dimensions. We're just going to substitute that value into our volume formula, pi to the n over 2 divided by the gamma function of n over 2. Just 1 sec. N over, just 1 second here. Like words are funny sometimes. N over 2 plus 1. Okay. All right, so then what we're going to get here is that V at n equals 10, V of 10 is equal to pi to the power of 10 over 2, okay, divided by the gamma function of, well, n is 10, substitute in 10 divided by 2 plus 1. Okay, so we have that. So now this is the easiest part of this live session, as you can see, right? Is instead of talking about it conceptually, now we're just doing it numerically, right? Just very basic calculation, right? So as long as you're able to do BEDMAS, anyone can do this. Okay, so V of 10 is equal to pi to the 5th power, right? 10 over 2, 5, okay? Divided by gamma function of 10 over 2, which is 5 plus 1. As you can see, I'm doing everything slowly, right? Step by step, even though I could have calculated everything in one go, I'm doing it slowly just to show you all of my steps. Now, V of 10 would be pi to the 5th power, okay? All divided by the gamma function of 6. All right, so we have pi of 5th divided by the gamma of 6. All right, now we can calculate this, right? We can figure out what this is. Okay, so first we can figure out what gamma of 6 is. Okay, now it's very easy to figure out what the gamma of 6 is. Okay, as long as you know what a gamma function is. So for those of you who are new to my channel or my live streams, you may be new and you may already be very fluent at integral calculus and any other or taking any mathematical methods classes. That's another thing too. Then you should be able to do this very easily. But if you're new and you have no background or very low background in integral calculus or any other form of math, this would be a problem. Okay. But if you know factorials, as long as you know some basic probability that you've taken in high school, grade 11 or 12 probability, because they talk about that, they do that section in math, you should be able to calculate this. Okay. So I'm going to put to the side here, right? Okay, so note. I just put it in red to bring home the point here. Note. The gamma function, okay, so gamma, right, so gamma of n, function n, is equal to n minus 1 in parentheses, all factorial, okay? For those of you who know factorials, you'll know how to compute this, right? All right. Factorials are used in probability a lot, actually. So, right? So, okay, so n minus 1 all factorial. All right, so we have that. So I'm just going to put this like this. This is, actually, you know what? Not just that. Gamma of n minus 1 all factorial. This is the gamma function at n. Okay, so I'm going to put right here. This is the gamma function at n, in factorial, whatever. Any questions? Anyone have any questions? Please give me questions. I don't like to ramble. Anyone have any questions on this or anything else? As I mentioned, this is your chance to ask me not just questions on this, but any math, physics questions that you find very hard in your classes, or problems that you may be reading for your self-interest and you need help with. Anything. Let me know any problems at all. Okay, if not, anyway, questions. Okay, if not, then we can go back because we have to talk about something. So if there's no questions that you guys are struggling with, we'll go back to the topic at hand. So the gamma function of n, right, is equal to n minus 1 factorial. So for instance, if n is 6, okay, we're just going to substitute that into our formula. Okay, so substituting at n equals n is 6 in this case. Now, don't get confused. This n is not the same n of the original problem. Okay. All right. That n was the n of the dimensions, number of dimensions that we're dealing with. This n is the n of the gamma, right? Right. So quite often we use n. We could have used p or whatever. Maybe I should say p, so it's not as confusing, right? Yeah, I'm going to use p here. So let's say gamma of p, right? Gamma of p is equal to p minus 1 factorial. P minus 1 function at p, where p is a number inside the gamma function, okay? So p is a function number inside the gamma function. It's not the same as n number of dimensions. So computing that, right, we get v of 10. Now, let's do that. So that's pi to the 5th power. I'm going to take care of that in a second. I just want to calculate this is 6 minus 1 factorial. 6 minus 1 factorial. Then we're going to be left with pi to the 5th power over, what's that? Yeah, that's 5 factorial. Okay. All right, so that's straightforward. There shouldn't be any dispute with that. Okay. Then from here, you will notice that pi to the 5th all over 5 factorial. 5 factorial is just 5 by 4 by 3 by 2 by 1, right? Okay. N factorial is always n times n minus 1 times n minus 2 times n minus r plus 1. Right? So you're always multiplying n minus 1 of the previous product term that you were calculating, okay? All right, so it's 5, then it's subtract 1, 4, multiplied by subtract 1. Again, 3, multiplied by subtract 1, 2, and 1. Good. So you should get pi to the 5th power, right? Pi to the 5th power divided by 5 by 4, that's 20. 20 times 3, okay? That's 60. 60 by 2, 120. So far, we have a ratio of pi to the 5th power divided by 120. Anyone have questions? Any questions? Doesn't have to be on this. As I said, it could be math, physics related. Give me your hardest problems. I'm a person who thrives on challenges. Okay. And don't use ChatGPT. Quite often with more advanced mathematics, it's wrong. It can give you a very good framework when it comes to solving math problems. It's good for that, but it's not always right. right? You should be getting used to independently solving the problems yourself. In other words, you have to be struggling with the problem. That's the way you do math. You have to struggle with the problem. And if you've tried everything, you've gotten very annoyed, then ask for help somewhere. Okay. But don't always rely on technology for this, right? This would be a very, it's not as reliable. And it's screwing up your critical thinking skills, right? This channel is about improving your critical thinking skills, right? Not making them worse. Okay. So so if there's no questions, let's get back to the volume. Okay. So pi to the fifth over 120. Okay. Now I'm going to have to look into get my calculator out here. What's pi to the fifth? Excuse me. Sorry about that. Okay, so pi to the fifth power. So that's just saying 3.14 times 3.14 times 3.14 times 3.14, 234 times 3.14. Okay, so we got 305.244. 305.244. That's a decimal, by the way. I don't want that to be confused as a comma. Decimal. Okay, 305.244 divided by 120. Obviously, you can see that should be greater than 2. Remember, our simulation, it looks like it got it right, as I said. AI can be right too. But yeah, the AI simulation, I think, is correct, because if you look at our fraction 305.244 divided by 120, if I were to take 120, go into 240, that'll give me a factor of 2. Since the numerator is greater than 240, that's 2 point something. So this should give us a value. Let's see what that value is. Okay, I'm just calculating. We're divided by 120. Yes, and we get 2.543. So yes, it looks like our AI got it correct. So 2.54. Okay, so 2.54 is the volume at n equals 10. So the volume at n equals 10 hyperdimensions of a sphere is 2.54. Okay. Right. So my point is, as I was saying earlier about AI, trust me, I'm into AI myself too. I use it for a lot of things, and it can be used as a framework and as something that can create content and can create simulations. I use it for simulations and stuff like that, and give you frameworks for problem solving and thing. But it is not to be a replacement for your mind. Your mind needs to still be able to solve problems independently, right? It's just a framework, right? So I use it as a framework, right? But as you can see, there's a difference between using it as a framework and being replaced. And that's what's going to happen, I think, to, unfortunately, to a lot of people if they don't start getting their act together, okay? What I mean by that is that using it as a framework means that you're taking into consideration what it says, you're using it for your work, but you're questioning it. And what I mean by questioning it, I verified my calculations. I didn't just say, okay, it's 2.54, let's take it for what it is. I wanted to verify it using reasoning, okay? Using numerical reasoning, right? In this case, or logical reasoning, or any other form of reasoning, right? So you won't be replaced, because there's a lot of thing going on lately that people are afraid that they'll be replaced, right? In reality, no job is safe from this, and no job is unsafe from it, right? It's not like a specific job that's going to be replaced by this technology. It's what you do as a person that's going to replace you, right? So if you are taking the information and you're not questioning what it's saying, then you have a higher chance of being replaced. at your work or at anywhere where you're in a job type of situation and you have a hiring manager or whatever. I know I'm getting off topic. This is a math channel, but um, but yeah, since we're talking about AI, I thought I'd bring it up, right? So you need to make sure that you're using it as a framework, but you're not using it for replacement. It's not to replace your critical thinking, right? Because it, if you do that, not only you be replaced with any job that you're doing eventually, because it's going to be everywhere in industry, okay? Because your bosses will say, well, if you're just using it just like that, mindlessly, why do I need you? Okay? Um, but not only that, a problem, your critical thinking skills will plummet to the ground. Okay, so use it as a framework, not as a replacement for your logical thinking. Okay, all right. So let me see if anyone on the desktop have questions. So if there's nobody else asking questions, I think I'll end it here. Okay, for the live stream. Uh, I hope you've enjoyed it. For those of you who have joined, uh, for anyone else who has interest in this stuff, as I mentioned, if you are interested in advanced integration techniques, whether you're a person who likes to learn complicated, who has a background in integral calculus and linear algebra, and either wants to learn more mathematical methods to build up on the knowledge you have, this is the book for you. Or if you're a person who likes real complicated challenges and uh, already has a very, very, very strong background in mathematics, there's a section for open-ended problems. That means problems that not even I can solve. But yes, that will be. This is the place to be. There'll be plenty of more videos and live streams coming up. I plan to make the simulations interesting as usual, and uh, that will be it. Thanks again for joining. Like and subscribe, new viewers, and I will see you next time. Bye bye.